So now if you want to solve our elliptic equations using the finite difference method, we're going to use the central difference equation on some grid to solve the equation. And we're going to work almost in the exact opposite direction to what we just worked through in our last video. That is, we initially started with a grid and we derived the equation. Now we're going to look at the equation and solve it on our grid. Okay, so what do I mean by this? Well, we have some grid. Let's just put some grid points here. Okay, and the spacing in this direction is delta y, and the spacing in this direction is delta x. Okay, so our coordinate system is vertical is y, horizontal x. Okay, now let's just label these grid points. So if I label this central one I, and then this to the right, so it'll be I, j, then this is going to be I plus 1, j, I minus 1, j, this is going to be I, j plus 1, and I, j minus 1. Okay, so now we could use the central difference equation to solve for our two parts of our elliptic equation. So that is day squared. I'm just going to use phi instead of h. So day squared phi day x squared using central difference can be approximated as phi I plus 1 j minus 2 phi I j plus phi I minus 1 j, that all divided by delta x squared. And then in the y direction we have day squared phi day y squared is phi I j plus 1 minus 2 phi I j plus phi of I j minus 1 over delta y squared. Alright, so if delta y equals delta x, then we have the following. That is phi I plus 1 j plus phi I minus 1 j plus phi I j plus 1 plus phi I j minus 1 minus 4 times phi I j equals 0. Okay, in other words, we take a single contribution from the grid point above our central one, single one to the left, single one to the right, single one below, and we take minus 4 in the center. Alright, so if this term on the right here, this phi term, is known as the Laplace operator, and if we specify boundary conditions or at the boundary points to our grid, we can then solve for a unique solution. And the simplest boundary condition we can apply is just by setting some value at the boundary, and this is known as the Dirichlet boundary condition. So with m interior nodes in the x direction and n interior nodes in the y direction, we have m plus n linear simultaneous equations for which the unknowns can be solved using our standard methods which we've learned so far. So let's look at an example and apply this solution technique.